Welcome back, students. Before the semester ends, we want to delve into NMR a little bit. This is probably the most abundant spectroscopy you've used up to this point in your chemistry careers, and we want to look into this a little bit and understand how this works. Recall that this was probably the most helpful spectroscopy technique we used in organic chemistry. Think back to all your unknown labs and so forth. And we can almost single-handedly figure out what a molecule is simply by looking at its NMR spectra. So we'll remember, going back to organic chemistry, that NMR depends on this thing called chemical shift. And we have electron withdrawing groups, and that shifts the signal we get from NMR. And then we also have these peak splittings, depending on the number of hydrogens that are near the hydrogens that we're looking at. So we'll start today by thinking about the chemical shift and what the chemical shift is. And then in the next lecture, we'll look at what causes the peak splitting and how we can figure out what the peaks are due to. And a lot of this you'll be familiar with from organic chemistry, but here we're looking at why these things happen. So we already know that they do happen, and we want to understand physically what's going on here, what makes these things happen. So the learning goals for today are going to be to apply spin angular momentum operators to nuclei rather than electrons. And these are going to have the exact same forms as every spin angular momentum operator that we've had, whether it was orbital or electron spin. Then we're going to figure out what the magnet is doing in the NMR. So we also know that NMR has something to do with big magnets, and we'll figure out what that is doing. And then we'll use all of these things, put them together, and figure out what a chemical shift is. Okay, so it turns out that atomic nuclei also have intrinsic angular momentum, just like electrons have this intrinsic angular momentum. And it actually turns out that only some nuclei have intrinsic spin or intrinsic angular momentum. And the reasons for this is complicated, and you have to go down and talk to the physics guys to figure out why this is the case. It's more like nuclear physics. But we can look at this in terms of basically the number of protons and neutrons. If a nuclei has an odd number of protons or neutrons, it will have some intrinsic spin. So our favorite spinning nuclei from organic chemistry is going to be the H1 atom. So H1 atoms or nuclei have an intrinsic spin that has a 1/2 quantization, just like electrons. Other nuclei can have more complicated spin. So you see deuterium, H2, has a spin of 1, N14 has a spin of 1, and as it has 7 protons and neutrons, and different other elements in nuclei can also have different spins. Now, it's important that our most abundant nuclei in organic molecules, carbon-12 and oxygen-16, have no spins. They're not NMR active, and typically, you'll remember this from organic chemistry, we only look at H1, so we do H1 NMRs. And you can, of course, do different kinds of NMR, and that's going to be more complicated than we want to get into. But there are other types of NMR that you can do, and you can even bounce these things off each other, make 2D NMR, and so forth. So what we're talking about here is a nuclear magnetic moment or a nuclear spin. And just like all of our other spins, this is due to having some angular momentum. So we have angular momentum operators for the nuclear spin. And these angular momentum operators have the exact same form as we've seen before. So we're going to be specifically considering hydrogen nuclei, and that is because they have the spin up and spin down. If your spin is quantized in terms of 1/2, we can talk about that as spin up or spin down, just like for electrons. If you have different quantization for nuclear spin, you have more options, and spin up and spin down isn't enough to talk about these things. But for the hydrogen nuclei, it is. And so we have these operators that determine the magnitude of the angular momentum, and then also the z component. And this has the exact same form as we've seen it every other time it has appeared. So we have an alpha, which is spin up. We have a beta, which is spin down. And the magnitude of these nuclear momenta are 1/2 times 1/2 plus 1 times h bar squared times alpha again. And the z components are simply 1/2 h bar times alpha. And then if we have the spin down, it's minus 1/2 h bar. So these operators are going to obey all of the same rules as our past angular momentum operators. They're doing the same thing. And in the case of hydrogen nuclei, the eigenfunctions function the same way as our electrons. We have an alpha spin up and a beta spin down. We can calculate the nuclear angular momentum, and this is related to the nuclear magnetic moment. And we can calculate this in the following way. So our nuclear magnetic moment mu here, and this is in bold to show it's a vector, is equal to a couple of constants multiplied by I, our orbital, or not our orbital, but our nuclear angular momentum. The first constant here is Gn. This is called the G factor, and it's a constant for every different nucleus. Then we have this factor here, which will combine into this beta n term. And so this is the charge, so the fundamental charge times Planck's constant over 2 pi divided by 2 times the mass of the proton. And that gets us this beta constant here. And often these are put together into this gamma. And gamma is called the magnetogyric ratio. And so this magnetogyric ratio is going to be different depending on the nucleus involved, and it will give us a variety of different nuclear magnetic moments. That's going to depend on the quantization and so forth. So our magnetic moment has a units of amp meters squared, which we can also convert into joules per Tesla, where Tesla is the unit of magnetic field. So we'll see magnetic fields are going to come into play here, as of course they do for NMR. We have our beta and our nuclear magneton and our gamma, our magnetogyric ratio. And we can see that there's a lot of different G factors. So for hydrogen, it has a very large one, and other atoms have smaller ones. And we can put these things together to get the magnetogyric ratio here. And so this will allow us to calculate the strength of the magnetic moment. Now, this is going to be important because this nuclear magnetic moment is going to interact with a magnetic field, and we're going to have this magnetogyric ratio is going to appear in our future equations. But the focus, we're doing a little bit of math here, but keep your focus on the concept. We're trying to figure out what NMR is and what's happening in NMR. So the next question that hopefully you would ask is, what's the difference between having a nucleus spin up and spin down? For electrons, there wasn't really anything that went on there. If we had a spin up electron, we would pair that with a spin down electron, but there was not really a difference in energy between having an electron spin up and an electron spin down. So why would that be the case for nuclei? And it turns out that the answer is normally there is no difference between spin up and spin down. And in order to see a difference between spin up and spin down nuclei, we have to apply an external magnetic field. So the external magnetic field is what causes the spin up and spin down nuclei to have different energies, and we can actually see these transitions between them using NMR. So without the big magnet, we don't see differences in energy, and we can't do NMR. Now, what happens is that the energy here, so E is for energy, is equal to the negative of our magnetic moment, and then times B naught, where B naught is the applied external magnetic field. And we can break this down into the following here. So the energy is going to be equal to plus or minus H bar times gamma times B naught, depending on if our nucleus is in spin up or spin down. So what this tells us is that if we have no applied external magnetic field, there is no energy associated with having spin up or spin down. And if we do, there is one depending on the strength of B naught. So it also, the stronger B naught is, the greater the separation. And this is why we want bigger and bigger and stronger magnets for NMR. The stronger your magnet, the larger you can get this difference and the more resolving power you will have. So what we end up seeing under the applied magnetic field is we have two different energies and they get increasingly different. Separation gets larger and larger, the stronger B naught our applied magnetic field is. What will happen when we look at this in terms of what's happening in the bulk solution is that our molecules will align themselves with the magnetic field. And this will give, on average, more molecules having spin up. So more of our molecules will have a spin up here, and less will have a spin down because the spin up is lower in energy. And if we look on average, what's going to happen is that the X and Y components end up canceling out as they're tumbling in solution. So we only are going to be considering the component that lines up with the magnetic moment or the applied magnetic field, which in this case is the Z direction. So the next thing we'll want to do is figure out the energy difference between these two. And that's going to tell us what kind of energy we need to excite. So hopefully I'll let you guys pause the video and go back and do this math here to figure out what the delta E is. So this E is going to be the energy of the beta state and the alpha state, depending on if it's plus or minus 1/2. And so the difference between them is simply going to be H bar times the magnetogenetic ratio times the applied magnetic field. So go ahead and solve this if we have an applied magnetic field of 5.5 Tesla. All right, so if you multiply the magnetogyric ratio from a couple slides ago, well, actually, let me redo this. So let's go back, and what we're going to do is multiply gamma. So we'll go back and see what gamma is. Gamma for hydrogen is 26.75, and this is times 10 to the 7th. That's right. Okay. Resuming in 3. So let's go back and calculate the change in energy between the beta state and the alpha state. That's simply going to be H bar gamma times B naught. So we'll use a B naught of 5.5 Tesla. Now let's go back and so we can see this gamma, the magnetogyric ratio. For hydrogen, that's 26.75 times 10 to the 7th. So we'll take 26.75 times 10 to the 7th, multiply that by Planck's constant and 5.5 Tesla to figure out the change in energy between the alpha state and the beta state. Now, with that done, hopefully what you got was a value of 1.55 times 10 to the minus 25 joules. This can be kind of hard to imagine what this is. We're not used to thinking of these things in energy. If we convert this into a wavelength, we find out that this wavelength is on the order of 1 meter. So this is a very, very low energy light, a very high wavelength light that excites this transition. And these are in the radio wave frequencies. Now, what does this mean for our populations? Before, we've used the Boltzmann distribution to figure out how many of our molecules are in the excited state compared to the ground state. And with something like IR spectroscopy, it was mostly in the ground state. For something like rotation that was in the microwave energy range, it was not mostly in the ground state. They were mostly in excited states. So in this case, using radio waves, we're going to be essentially 50-50. And you can go ahead and do these sorts of calculations if you want. In this case, delta E is much lower than KT, meaning we have approximately even distributions. And that is what makes these transitions actually hard. So the larger and stronger the magnet is, the more separation we can get and the more molecules we can actually get in the ground state compared to the excited state, which makes transitions easier to observe. Now, how we actually observe these transitions is using radio wave frequencies. And these radio wave frequencies are shot perpendicular to the applied magnetic field, and those are actually involved in transitioning the molecules. So the applied magnetic field, the big strong NMR magnets, don't do the transitions. The big strong NMR magnets make differences between excited states and ground states, having spin up or spin down, and then we can hit them with low energy light with radio waves in order to actually excite those transitions. That's what's going on in the NMR instrument. The last thing we'll want to think about is what is chemical shift and what is the origins of chemical shift. So we're going to imagine an atom that's in this applied magnetic field. Now, this atom is not a nucleus. If the atom was a bare nucleus, we would just have the applied magnetic field here. But there are electrons. And of course, electrons are going to interact with an applied magnetic field. And we can think about these electrons interacting with the applied magnetic field by physically spinning. Now, what does that do? When you have an electron, I think with a charge that's spinning, that induces another magnetic field in the vicinity of the nucleus. And the way that this induces a magnetic field is by these circles that we can see here. So we see these kind of circles. This is the induced magnetic field that's based on the electrons around the nucleus of our atom that are interacting with the magnetic field. Now, what does this do? If we look at the nucleus itself, we see that the electrons are coming down, the applied magnetic field from the electrons is coming down, exactly countering the applied external magnetic field. So in this case, the induced magnetic field reduces the applied magnetic field. And we can talk about the total magnetic field felt by the nucleus as 1 minus sigma, where sigma is this shielding based on the number of electrons. So the more electrons there are, the larger the shielding is, and the more applied magnetic field is reduced. Now, what does this do? Remember, the separation in terms of alpha and beta is based on the magnetic field felt at the nucleus. So if we change the magnetic field felt at the nucleus by having electrons around the nucleus, we shift physically down our energy here, and that means the transition would be less. So if we started here, if this was our delta E under a bare magnetic field, if we have electrons, that reduces the magnetic field, the transition is going to be lower. And so an atom with an electron would have a lower energy transition than an atom without an electron. Now, of course, when we look at molecules and hydrogen atoms, they only have one electron. But hydrogen atoms have electron withdrawing groups. And these electron withdrawing groups withdraw electron density. And what we have around hydrogen atoms is different amounts of electron based on the nearness of electron withdrawing groups. And this gives rise to chemical shifts. So depending on the electron withdrawing groups around your hydrogen atom, they have more or less of their electron density associated with them, and they have a different signal. And so specifically in this case, we'll think about the frequencies involved in the transition. And the frequencies involved in the transition are equal to the following. So we have a shift in frequency that's due to sigma v or sigma gamma times b naught over 2 pi. So depending on the shielding, depending on how much electron is around here, we can shift the frequency to lower wavelengths. Now, what we'll do is apply this to chemical shift. We'll have this formula here where our chemical shift is in delta, and our delta is equal to 10 to the 6, and this 10 to the 6 is just scaling to get it into numbers that we like to look at, like 1, 2, 3, 10, that kind of stuff, because the shifts are pretty small. And then what we have is our actual shift, so this is our new frequency, and then minus the reference. So this should be having some standard. So the standard we usually use is TMS, tetramethylsilane, which is a silicon atom with 4 methyl groups attached to it. And that's chosen as having a hydrogen with full electron density. And so we can get a chemical shift by having shifts from this full density. And we choose having positive chemical shifts to mean that we have less electron density here. So if we look at the 0 point would be our tetramethylsilane. Methyl groups where hydrogens still have about the same amount of electrons have a chemical shift of 1. And then methylene is a little bit less as they're having less. Acetylene down here and so forth. So we can see that there's ranges of chemical shifts based on the electron withdrawing groups around these molecules. And so the less electrons there are around hydrogen, the larger the chemical shift that we see. And with this, we'll take a break here, and we'll pick up next time by looking at, we'll continue looking at NMR and talking about multiplet splitting and what gives rise to that. So I'll leave it here, and I'm looking forward to talking about this with you guys in class.